Hello everyone, today we'll study the inverse trigonometric functions. Those are the inverse trigonometric functions. Let's read inverse of sine, that's inverse of cosine, that's inverse of tangent, that's inverse of cotangent, that's inverse of secant, and that's inverse of cosecant. Now, what does the inverse function mean? Let me give you some rough idea about inverse functions. Some rough idea. In general, the inverse trigonometric functions do the opposite of the corresponding trigonometric functions. In general, the inverse trigonometric functions do the opposite of the corresponding trigonometric functions. For example, we know that sine of 30 degrees is a half. Sine of 30 degrees is half. That means inverse sine of a half is 30 degrees. Sine function takes 30 degrees to half. Inverse sine function take half back to 30 degrees. So for sine function, we input angle, get a real number. For inverse sine function, we input a real number and get an angle. For sine function, we input angle measure, get a real number. And for inverse sine function, we input a real number and get an angle measure. This angle measure, it could be either in degree measure or in radian measure. 30 degrees is the same as pi over 6. So for trigonometric functions, we input a degree measure, we input angle measure, get a real number. And for inverse trigonometric functions, we input a real number and get angle measure. This angle measure, it could be either in degree measure or radian measure. Another example, say cosine of 30 degrees. Cosine of 30 degrees is radical 3 over 2. Here, cosine function takes 30 degrees to this real number. Inverse cosine function does the opposite. It takes radical 3 over 2 to 30 degrees. Another example, tangent takes 30 degrees. Let me give you some different values. Tangent takes 45 degrees to 1. Tangent 45 degrees is 1. Inverse tangent does the opposite. Inverse tangent take 1 back to 45. So tangent take this angle measure to 1. Its inverse function take number 1 back to this angle measure. For example, cotangent of 60 degrees. Cotangent 60 degrees is 1 over radical 3. Its inverse function does the opposite. Its inverse function take 1 over radical 3 back to 60 degrees. Secant function. For example, secant function take 45 degree angle to radical 2. Its inverse function will take this real number back to 45 degrees. its inverse function, take radical 2 back to 45 degrees. Another example, cosecant of 30 degrees is 2, which means its inverse function take 2 back to 30 degrees. That's how inverse function works. But those are just some examples. Those are some rough ideas. However, if we think of the inverse trigonometric functions in this way, there is one problem. For example, we know that sine of 30 degrees is a half, which means inverse sine of half is 30 degrees. Since sine function takes 30 degrees to a half, inverse sine function take a half back to 30. So inverse sine of half is 30 degrees. However, how about sine of 150 degrees? How can we find sine of 150 degrees? We know that 150 degrees is an angle lies in quadrant 2. 150 degrees lies in quadrant 2. If an angle lies in quadrant 2, its reference angle is 180 minus angle itself. 180 minus 150 is 30. So that's its reference angle. For 150 degrees, its reference angle is 30 degrees. And we know that sine function in quadrant 2 is positive. So sine of 150 is the same as sine 30. And we know that sine 30 is a half, which means sine of 150 is a half. Sine function take 150 to a half. Then using the same idea, since sine of 150 is a half, inverse sine of a half should be 150 degrees. Since sine of 150 is a half, then inverse sine of a half is 150 degrees. Now do you see a problem here? Inverse sine of half is 30, inverse sine of half is 150. We know that as a function, for every input, we cannot get two different outputs. As a function, for every input, we cannot get two different outputs. So it doesn't work this way. That's a problem. It doesn't work in this way. Now, how can we fix this problem? As a function, for every input, we cannot get two different outputs. How can we fix this problem? We know that the graph of sine function looks like this. The graph of sine function looks like this. The first period is from 0 to 2 pi. What's in the middle is pi. And between 0 and pi, we have pi over 2. At pi over 2, sine function reaches its maximum at 1. What's between pi over 2 and 2 pi is 3 pi over 2. At 3 pi over 2, sine function reaches its minimum at -1. That's the first period. And there's more periods before the first period. For example, the graph looks exactly the same before 0. From -2 pi to 0, the graph looks exactly the same. From -2 pi to 0, the graph looks exactly the same. The midpoint between 0 and 2 pi is -pi. And the midpoint between -pi and 0 is -pi over 2. So at -pi over 2, sine function reaches its maximum at -1. Between -2 pi and -pi, the midpoint is negative 3 pi over 2. At negative 3 pi over 2, sine function reaches maximum at 1. Now, in order to define inverse sine function, we take this piece. In order to define inverse sine function, take this piece. From negative pi over 2 to positive pi over 2. We take this piece to define the inverse sine function. So for inverse sine function, take this piece. We define inverse sine function based on this piece. That guarantees for every input, there's exactly one output. For inverse function, take this piece. Interchange the x and y intercepts. Interchange the x and y values. For this curve, interchange the x and y coordinates. So the y coordinate is from negative 1 to 1. For the inverse function, y coordinate becomes x coordinate. Since we interchange x and y coordinates. Since the y value varies from negative 1 to 1. For the inverse function, x value varies from negative 1 to 1. And since x value varies from negative pi over 2 to pi over 2, for the inverse function, the y value varies from negative pi over 2 to pi over 2. This point is pi over 2 comma 1. For the inverse function, it becomes 1 comma pi over 2. This point is negative pi over 2 comma negative 1. For its inverse function, it becomes negative 1 comma negative pi over 2. Interchange x and y coordinates. Then flip the graph over the line y equal to x. Flip this graph over the line y equal to x. Flip this graph over the line y equal to x. It looks like this. So that's the graph of inverse of sine. Based on this graph, this one piece of sine function. This is not the entire sine function. This graph contains only one piece of the sine function. We find the inverse of sine function based on this piece. Now, based on this graph, we can see that for inverse sine function, its domain is from negative 1 to 1. Including the endpoints. Its range is from negative pi over 2 to pi over 2. Including the endpoints. That's inverse sine function. That's inverse sine function. Next, we define inverse of cosine in a similar way, in a very, very similar way. Next, we define inverse of cosine in a very, very similar way. We know that the graph of cosine looks like this. Its first period is from 0 to 2 pi. The graph looks like this. It starts from 1. It goes down first. At pi, it reaches negative 1. Then it bounces back. At pi over 2, it goes back to 1. That's the cosine function in the first period. And we know that the cosine function repeats itself before and after the first period. So from 0 to negative 2 pi, the graph looks exactly the same. From 0 to negative 2 pi, the graph looks exactly the same. and negative pi, it reaches the minimum at negative 1, and negative 2 pi, it goes back to 1. That's the graph of cosine. Here, the x-intercept here is pi over 2, 3 pi over 2. On the other side is negative pi over 2 and negative 3 pi over 2. Now, for inverse of cosine, we take this piece. Take the piece between 0 and pi. For inverse cosine, we find the inverse cosine based on this piece from 0 to pi. For inverse cosine, we find the inverse function based on this piece from 0 to pi. That guarantees for every input there's only one output. This situation won't happen. That guarantees for every input there's only one output. So for inverse cosine, take this piece. Next, we interchange the x and y coordinates. For inverse function, we interchange the x and y coordinates. Here for this piece, x coordinates varies from 0 to pi. So when we find the inverse function, the x coordinate becomes a y coordinate. So the y coordinate varies from 0 to pi. We interchange x and y coordinates. Since the x coordinate varies from 0 to pi, the y coordinate from the inverse function, the y coordinate varies from 0 to pi. Now for cosine function, since the y coordinate varies from negative 1 to 1, for its inverse function, the x coordinates varies from negative 1 to 1. X-intercept here is pi over 2. So the y-intercept here will be pi over 2. When we find the inverse function, the x-coordinate becomes a y-coordinate. This point is 0, 1. This point is 0, 1. For the inverse function, it becomes 1, 0. We interchange the x and y coordinates. This point is 0, 1. For the inverse function, it becomes 1, 0. That's this point. This point here is pi, negative 1. This point here is pi, negative 1. For the inverse function, we interchange the x and y coordinates. So it becomes negative 1, pi. That's this point. Then flip the graph over the line, y equal to x. Flip this graph over the line, y equal to x. Again, the inverse function, it looks like this. That's the graph of inverse of cosine. For this graph, we can see that the domain of inverse cosine is from negative 1 to 1. The domain of inverse cosine is from negative 1 to 1. The range is from 0 to pi. The range is the y coordinate. It's from 0 to pi. That's the inverse cosine. Next, let me show you how to define inverse of tension. First of all, the graph of tension looks like this. In the first period, we have vertical asymptotes at negative pi over 2 and pi over 2. That's the first period. That's the graph in the first period from negative pi over 2 to pi over 2. Its graph looks like this. Then the same graph repeats itself for the next period. Next period is from pi over 2 to 3 pi over 2. That's another vertical asymptote. What's in the middle is pi. And there's another period before the first period. It's from negative 3 pi over 2 to pi over 2 negative pi over 2. The point here is negative pi. The same graph repeats itself. And there are infinitely many such pieces. There are infinitely many such pieces. For the inverse of tension, we take the first piece, we find the inverse based on the first piece, based on the piece in the middle. For inverse tension, we take this piece in the middle and find the inverse function. For this piece here, for this piece in the middle, there are two vertical asymptotes. When we find the inverse function, we interchange the x and y coordinates. So vertical asymptote become horizontal asymptotes. When we find the inverse function, these two vertical asymptotes become horizontal asymptotes. So for inverse tension, there are two horizontal asymptotes at negative pi over 2 and positive pi over 2. Assume that's negative pi over 2 and that's positive pi over 2. There are two horizontal asymptotes. There are two horizontal asymptotes. Now for the inverse function, we flip the graph over the line y equal to x. Flip the graph over the line y equal to x. Flip this graph over the line y equal to x. So this piece looks like this. This piece for the inverse function looks like this. This piece looks like this. That's the inverse of tension. For this graph, its domain the domain here contains all real numbers. The domain is itself all possible x values. Here the domain contains all x values. So domain is itself all real numbers from negative infinity to infinity. The range is from negative pi over 2 to pi over 2, and the endpoints are not included. Range is the y coordinates from negative pi over 2 to pi over 2. The endpoints are not included. We cannot include asymptotes. Now, for this graph, there are two horizontal asymptotes. For tension, for inverse of tension, there are two horizontal asymptotes. There are two horizontal asymptotes at y equal to pi over 2 and y equal to negative pi over 2. There are two horizontal asymptotes at pi over 2 and negative pi over 2. For this graph, we have two n behaviors. For this graph, we have two n behaviors. We have two n behaviors. As x approaches to negative infinity, As s approaches to negative infinity, y approach to negative pi over 2. As s approaches to negative infinity, y approach to negative pi over 2. As s approaches to infinity, y approach to pi over 2. Those are and behaviors of tension, of inverse of tension. Next, let me show you the inverse of cotension. The graph of tension, the graph of cotension looks like this. Let me graph cotension first. The graph of cotension looks like this. It's very similar as tension. For cotension, we have vertical asymptotes at 0 and pi. That's the first period. We have vertical asymptotes at 0 and pi. That's the first period. What's in the middle is pi over 2. The graph looks like this. The graph in the first period looks like this. And the next period is from pi to 2 pi. That's another vertical asymptote. The midpoint here is 3 pi over 2. And the period before the first period is from negative pi to 0. That's the period before the first period. It's from negative pi to 0. The vertical asymptote is negative pi. The vertical asymptote is s equal to negative pi. The midpoint here is negative pi over 2. That's the graph of inverse cotension. And there are infinitely many such pieces. For the inverse function, we'll only take this piece, the piece in the first period. For inverse cotension, only take this piece, and for the inverse function. For inverse cotension, only take this piece, and for the inverse function. Next, let me show you the graph of inverse cotension. For the graph in the first period, there are 2 vertical asymptotes at 0 and pi. If I interchange the s and y coordinates, vertical asymptotes become horizontal asymptotes. So there are 2 horizontal asymptotes at 0 and pi. There are 2 horizontal asymptotes at 0 and pi. S-intercept here is pi over 2. When I interchange the s and y coordinates, s-intercept become y-intercept. So y-intercept here is pi over 2. Those are the horizontal asymptotes. Next, find the graph of an inverse function. We flip the graph over a line. Flip this graph over a line, y equal to x. For an inverse function, flip the graph of this line. Flip this graph over a line, y equal to x. So the graph of inverse cotension looks like this. If I flip this piece over, I get this piece. Next, if I flip this piece over, I get this piece. That's the graph of the inverse cotension function. Based on this graph, we can tell that the domain of inverse cotangent is the set of all real numbers from negative infinity to infinity. The set of all real numbers from negative infinity to infinity. The range of inverse cotangent is from 0 to pi, not including 0 and pi. The range is the set of all y values from 0 to pi. And there are two horizontal asymptotes. For inverse cotangent, there are two horizontal asymptotes. Y equal to 0 and y equal to pi. There are two horizontal asymptotes, y equal to 0 and y equal to pi. And for this graph, there are two end behaviors. We have two end behaviors, the left end and right end. On the left side, as x approach to negative infinity, as x approach to negative infinity, y approach to pi. On the right side, as x approach to infinity, y approach to 0. As x approach to infinity, y approach to 0. That's the graph of inverse cotangent. Next, I'll show you the inverse of secant. Let's take a look at secant function first. The graph of secant looks like this. It has vertical asymptotes at negative pi over 2 and pi over 2. Another asymptote at 3 pi over 2. One intercept here is 1. Another piece looks like this. Maximum is negative 1. It's open downward. Another piece is from negative pi over 2 to negative 3 pi over 2. That's a graph of secant. For inverse secant, we take this piece, only half piece here, this piece, from 0 to pi over 2. Take this half piece from 0 to pi over 2. Another half piece here, from pi over 2 to pi. For inverse function, we take this piece and this piece. Flip over, that's the inverse of secant. So for inverse secant, take this piece and this piece. Flip over the line, y equal to x. That's the inverse of secant. So the graph of inverse secant looks like this. For inverse secant, there's a vertical asymptote at pi over 2. If I interchange x and y coordinates, the vertical asymptote becomes a horizontal asymptote. So there's a horizontal asymptote at pi over 2. There's a horizontal asymptote at pi over 2. This point here is 0, 1. If I interchange the x and y coordinates, this point becomes 1, 0. If I interchange the x and y coordinates, this point becomes 1, 0. So 1 is here. This point becomes 1, 0. This point here is pi, -1. If I interchange x and y intercepts, this point becomes -1, pi. Assume pi is here. Then this piece will get closer to asymptote. This point is here. This piece flip over the line y to x. It must get closer to asymptote. It looks like this. This piece here, start from this point, and it must get closer to an asymptote. That's the second piece. So this is a graph of inverse secant. This is a graph of inverse secant. Based on this graph, we can find the domain and range of inverse secant. For inverse secant, the domain has two pieces. The domain has two pieces. First piece is from -infinity to -1. Second piece is from 1 to infinity. For the domain, there are two pieces. First piece is from -infinity to -1. Second piece is from 1 to infinity. First piece is from -infinity to -1, including -1. Second piece is from 1 to infinity, including 1. That's the domain of inverse secant. For the range is a set of all possible y values, all possible y coordinates. Here, y coordinate values from 0 to pi. Here, y coordinates values from 0 to pi, except pi over 2. Y coordinates values from 0 to pi, except pi over 2. So the range is from 0 to pi over 2, and then skip pi over 2, from pi over 2 to pi. The range is a set of all y coordinates, all y values from 0 to pi, except pi over 2. So it's from 0 to pi over 2, then skip pi over 2, from pi over 2 to pi. That's a domain, that's a range. There's a horizontal asymptote at y equal to pi over 2. There's a horizontal asymptote at pi over 2. Next, let me show you the inverse of cosecant. First of all, the graph of cosecant function looks like this. There are vertical asymptotes at 0, at pi, and 2 pi. And before 0, we have vertical asymptotes at -pi and -2 pi. That's the graph of cosecant function. That's the asymptotes. The graph looks like this. First piece has minimum at 1. It's open upward. Second piece has maximum at -1. It's open downward. That's the graph of cosecant in the first period, from 0 to 2 pi. And from 0 to -2 pi, the graph looks exactly the same. open downward, then the other piece is open upward. That's the graph of cosecant. For inverse cosecant, we take a half piece from here. Take half piece from here. Half piece from here. For inverse cosecant, we take half piece from here and half piece from here. Then flip over the graph over a line, y equal to x. We get the inverse of cosecant function. Next, let me show you the graph of inverse cosecant. Based on this piece, these two pieces, we can see that there's a vertical asymptote at 0, s equal to 0. If I change the s and y coordinates, the vertical asymptote becomes horizontal asymptote. So we have a horizontal asymptote at 0. This point here is pi over 2, comma 1. This point here is pi over 2, comma 1. If we change the s and y coordinates, this point becomes pi over 2, comma 1, become 1, comma pi over 2. Assume pi over 2 is here. 1 is here. That's the point 1, comma pi over 2. This point here is negative pi over 2, comma negative 1. If I interchange the s and y coordinates, it becomes negative 1, comma negative pi over 2. Assume negative pi over 2 is here. That's the second point. That's this point. Then flip the curve over the line, y equal to x. This piece looks like this. And this piece looks like this. That's a graph of inverse cosecant. Based on this graph, you can see that the domain is a set of all real numbers from negative infinity to negative 1, and then from 1 to infinity. There are two pieces. First piece is from negative infinity to negative 1, and then second piece is from 1 to infinity. That's a domain. And the range is from negative pi over 2 to pi over 2, except 0, because at 0 there's a horizontal asymptote. So the range is a set of all y values from negative pi over 2 to pi over 2, except 0. All y values from negative pi over 2 to 0, and skip 0. From 0 to pi over 2, that's a range. And that's a horizontal asymptote at y equal to 0. That's how we define inverse secant and inverse cosecant. But in general, let's put a star here. In general, for inverse of secant and inverse cosecant, there's no universal agreement. For inverse of secant and inverse of cosecant, there's no universal agreement. If you read some different textbook, they may define this inverse function in different ways. For inverse secant and inverse cosecant, there's no universal agreement. If you read a different book, they may define the inverse function of secant and cosecant in different ways. But according to our textbook, we define inverse secant and cosecant in this way. Keep in mind that for inverse secant and cosecant, there's no universal agreement. If you read a different book, they may be defined in a different way. But according to our textbook, inverse secant and cosecant are defined in this way. So only for our textbook, we define inverse secant and cosecant in this way. Memorize these graphs. Next, let me show you how to evaluate the inverse trigonometric functions. Let a be a positive value in the domain. Then, for example, how can we evaluate inverse sine of a half, for example? How can we evaluate inverse sine of half? Here, a represents a half. Now, if this value a is in the table, if half is in the table, we can use this table to evaluate inverse sine of half. According to this table, we know that sine of 30 is half. That means inverse sine of half go back to 30 degrees. Since sine of 30 is half, that means inverse sine of half go back to 30 degrees. So here, inverse sine of half is 30 degrees. In general, we prefer to use radial measure. 30 degrees in radial measure is pi over 6. For special trigonometry values, we prefer to use radial measure. So 30 degrees is the same as pi over 6. Another example. How can we evaluate inverse cosine of 1 over radical 2? Again, 1 over radical 2 is a special value on the table. For cosine function, 1 over radical 2 is here. Cosine of 45 is 1 over radical 2. Cosine of 45 degree angle is 1 over radical 2, which means inverse cosine function take 1 over radical 2 back to 45 degree. So inverse cosine of 1 over radical 2 is 45 degree. In general, for special trigonometry values, we prefer to use radial measure. 45 degree in radial measure is pi over 4. Next, how can we evaluate inverse tangent of 1? How can we evaluate inverse tangent of 1? Again, 1 is a special value on the table. For tangent function, 1 is here. Tangent of 45 degree angle is 1, which means inverse tangent take 1 back to 45 degree angle. So inverse tangent of 1 is 45 degree angle. And 45 degree is the same as pi over 4. For the special value on the table, we prefer to use radial measures instead of degree measure. Next, how about inverse sine of 2/3? For inverse sine of 2/3, for sine function, you can see that 2/3 is not on the table. If 2/3 is not on the table, for inverse sine of 2/3, we must use calculator here. So for inverse sine of 2/3, by using calculator, in my calculator I get 41.81 degree. That means sine of 41.81 degree is 2/3. So inverse sine of 2/3 is 41.81 degree. How about inverse cosine of 1 over 4? Again, for cosine function, 1 over 4 is not a special value on the table. So we must use calculator. Using calculator, inverse cosine of 1 over 4 in my calculator is 75.52 degree, which means inverse cosine of 1 over 4 is 75.52. Next, how about inverse tangent of 2? How about inverse tangent of 2? We know that for tangent function, 2 is not a special value. For tangent, number 2 is not a special value. If 2 is not a special value for tangent, we must use a calculator. In my calculator, inverse tangent of 2 is 63.45 degree. So that's by calculator, 63.43 degree in my calculator. So if a value is not on the table, we must use calculator to evaluate these inverse trigonometry functions. But if a value is on the table, we can use the table to find angle, to find degree measures, to find angles. And in general, we prefer to use radian measure instead of degree measure. If a value is on the table, we prefer to use radian measure instead of degree measure. Next, how can we evaluate inverse sine of negative a? Inverse tangent of negative a. Inverse cosecant of negative a. Inverse cosine of negative a. Inverse cotangent of negative a. And inverse secant of negative a. How can we evaluate these values? Let's look at the graph. The graph of inverse sine looks like this. That's the graph of inverse sine. It varies from -1 to 1. Lower bound is negative pi over 2. Upper bound is pi over 2. Here, a is a positive value in the domain. Suppose a is here. Then, the distance from a to the curve, this distance is inverse sine of a. This distance here is inverse sine of a. And we know that this graph is symmetrical over its origin. If negative a is here, this distance and this distance are exactly the same. But this point is below the x-axis. So this value is negative. So this value here is negative inverse sine of a. This distance and this distance are exactly the same. This is positive. This point is above x-axis. This is positive. And this point is below x-axis. This is negative. They are exactly the same, but this is positive. This is negative. So inverse sine of negative a is negative inverse sine of a. So inverse sine of negative a is negative inverse sine of a. For inverse sine, I can pull out negative sign. Next, how about inverse tangent of negative a? The graph of inverse tangent looks like this. That's a horizontal asymptote, a pi over 2 and negative pi over 2. That's inverse of tangent. Here, a is a positive value in the domain. Assume a is a positive value in the domain. Assume a is here. So this distance here is inverse tangent of a. This distance here is inverse tangent of a. Negative a is somewhere here. Negative a is here. We are looking for inverse tangent of negative a. We are looking for inverse tangent of negative a. We know that since the graph is symmetrical on origin, this distance and this distance are exactly the same. And this point is below x-axis, so this is negative. So this point here is negative inverse tangent of negative a. This point here is negative inverse tangent of negative a. So for inverse tangent of negative a, I can also pull a negative sign. I get negative inverse tangent of a. For inverse tangent of negative a, I can also pull a negative sign. I get negative inverse tangent of a. Next, for inverse cosecant of negative a, the graph of inverse cosecant looks like this. Pi over 2 is here. Negative pi over 2 is here. That's a horizontal asymptote. 1 is here. The first piece looks like this. Negative 1 is here. Second piece looks like this. That's the graph of inverse cosecant. Here, A is a positive value in the domain. A is a positive value in the domain. Assume A is here. Assume A is here. So this distance here, this distance is inverse cosecant of A. This distance here is inverse cosecant of A. Now if A is here, negative A is somewhere here. That's negative A. This point is inverse cosecant of negative A. This point is inverse cosecant of negative A. Here we can see that this graph is symmetrical over origin. So this distance here and this distance here they are exactly the same. Since this point is below x-axis, it's negative. So this point here is negative inverse cosecant of A. This point here is negative inverse cosecant of A. Sorry, this is negative inverse tangent of A. We pull a negative sign. This point here is negative inverse cosecant of A. So we get negative inverse cosecant of A. So for these three functions, inverse sine, inverse tangent, inverse cosecant, if the value inside the parentheses is negative, I can pull negative sign outside. For these three functions, inverse sine, inverse tangent, and inverse cosecant, if the value in the parentheses is negative, we can always pull a negative sign. Now, for inverse cosine, cotangent, and secant, it's a little different. How can we find inverse cosine of negative A? Let me graph the function for inverse cosine first. The graph of inverse cosine looks like this. Its values from -1 to 1. In the y-coordinate, it varies from 0 to pi. The y-intercept is pi over 2. The graph looks like this. Suppose A is here, because A is a positive value in the domain. Suppose A is here. Then this distance here represents inverse cosine of A. This distance here represents inverse cosine of A. Negative A is somewhere here. It's symmetrical. Negative A is somewhere here. How can we find this value here on the curve? we know that this graph is symmetrical over this point pi over 2. So this distance and this distance are exactly the same. This distance is the same as this distance. So this point is pi minus this distance. For this point, I can use pi minus this distance. And this distance is the same as this distance. That's inverse cosine of negative a. Inverse cosine of a. So for this point, we use pi minus this distance. This distance is the same as this distance here. That's inverse cosine of a. So for this point, use pi minus inverse cosine of a. So cosine of negative a, that's pi minus inverse cosine of negative a. Inverse cosine of a. So for inverse cosine function, if I pull out negative sign, I must add pi in the front. For inverse cosine of negative value, if I pull out negative sign, I must add pi in the front. Now how about inverse cotangent of negative a? Let me graph inverse cotangent first. The graph of inverse cotangent looks like this. Horizontal asymptote is 0 and pi. There are two horizontal asymptotes. This point here is pi over 2. The graph looks like this. That's the graph of inverse cotangent. Here, a is a positive value in the domain. Assume a is here. A is a positive value in the domain. This distance here is inverse cotangent of a. Negative a is somewhere here. This point is inverse cotangent of negative a. This point is inverse cotangent of negative a. How can we find this value here? We know that it's pi here. The value is pi here. This distance is the same as this distance. So this distance is inverse cotangent of a. So for this point, I use pi minus this distance. So this point here is pi minus inverse cotangent of a. So for this point here, I use pi minus this distance, and this distance is inverse cotangent of a. So for cotangent of negative a, it can be written as pi minus inverse cotangent of a. So for cotangent function, if I pull out negative sign, I must add pi in the front. If I pull out negative sign, I must add pi in the front. Now how about secant of inverse of a? Inverse secant of negative a. How about inverse secant of negative a? Let me graph inverse secant first. Graph of inverse secant looks like this. Pi is here, 0 is here. There's a horizontal asymptote at pi over 2. So 1 is here. Negative 1 is here. The first piece looks like this. That's one piece. Another piece looks like this. That's a graph of secant. That's a graph of inverse secant. That's a graph of inverse secant. Here, a is a positive value in the domain. assume A is here. So this distance here is inverse secant of A. This distance here is inverse secant of A. Negative A is somewhere here. It's symmetrical. Negative A is somewhere here. We are looking for this value on the curve. How about this value on the curve here? We know that pi is here. Pi is here. Pi is here. In order to find this value here, I can use pi minus this distance. In order to find this value, I can take pi minus this distance. And this distance is the same as this distance here. Curve is symmetrical over this point pi over 2. This distance is the same as this distance, which is inverse secant of A. So for this point, I take pi minus this distance. Take pi minus inverse secant of A. That's this value. So inverse secant of negative A is the same as pi minus inverse secant of A. So for inverse cosine, inverse cotangent, and inverse cosecant, when we pull out negative sign, we must add pi in the front. For inverse cosine, inverse cotangent, inverse secant, when we pull out negative sign, we must add pi in the front. For sine, tangent, cosecant, we can directly pull out negative sign. But for these three functions, inverse cosine, inverse cotangent, inverse secant, when we pull out negative sign, we must add pi in the front. So that's the rule. Keep it in mind. Next, let's look at some examples. Evaluate or simplify each of the following expressions. First example, inverse sine of negative 1 over radical 2. For inverse sine of negative 1 over radical 2, I can first of all pull out negative sign. I get negative inverse sine of 1 over radical 2. Remember, for inverse sine, inverse tangent, inverse cosecant, if the number inside the parenthesis is negative, I can pull it outside. I can directly pull it outside. So for inverse sine of negative 1 over radical 2, I can pull a negative sign. I get negative inverse sine of 1 over radical 2. And we know that inverse sine of 1 over radical 2, that's a special value on the table. Sine of 45 degrees is 1 over radical 2. Sine of 45 degree angle is 1 over radical 2. That means inverse sine function will take 1 over radical 2 back to 45 degree. So inverse sine function take 1 over radical 2 back to 45 degree angle. And in general, for special trigonometry values, we prefer to use radial measures. So negative 45 degree can be rewritten as negative pi over 4. That's how we simplify this expression. Next example. How about inverse tangent of negative radical 3? How about inverse tangent of negative radical 3? Inverse tangent of negative radical 3, I can first of all pull a negative sign. Write it as negative inverse tangent of radical 3. We know that for inverse sine, tangent, cosecant, I can always pull out negative sign. If the inside is negative, I can always pull out negative sign. Then we have negative inverse tangent of radical 3. For tangent, radical 3 is a special value. We know that tangent 60 degree is radical 3. Tangent of 60 degree is radical 3, which means inverse tangent will take radical 3 back to 60 degree. Inverse tangent will take radical 3 back to 60 degree. So inverse tangent of radical 3 is 60 degree angle. 60 degree angle in radial measure is pi over 3. So that's an answer for this expression. Next. How about inverse cosecant of negative 2. Inverse cosecant of negative 2. For cosecant function, we can do the same thing. If what's inside parentheses is negative, I can always pull out negative sign. I get negative inverse cosecant of 2. If what's inside the parentheses is negative, I can always pull out negative sign. I get negative inverse cosecant of 2. And we know that for cosecant function, number 2 is a special value. Number 2 is a special value. Cosecant of 30 degrees is 2, which means inverse cosecant will take 2 back to 30 degrees. Since cosecant of 30 degrees is 2, that means inverse cosecant function will take 2 back to 30 degree angle. So inverse cosecant of 2 is 30 degrees. Next, convert 30 degrees to radial measure. That's pi over 6. If we convert 30 degrees back to radial measure, that's pi over 6. So the answer is negative pi over 6. Next, how about inverse cosine of negative 1 over radical 2? How about inverse cosine of negative 1 over radical 2? We know that for inverse cosine, cotangent, secant, for inverse cosine, cotangent, secant, if I pull out negative sign, I must add pi in the front. When I pull out negative sign, I must add pi in the front. So inverse cosine of negative 1 over radical 2, if I pull out negative sign, it can be rewritten as pi minus inverse cosine of 1 over radical 2. And we know that for cosine function, 1 over radical 2 is a special value on the table. For cosine function, 1 over radical 2 is a special value on the table. Since cosine of 45 degree angle is 1 over radical 2, inverse cosine will take 1 over radical 2 back to 45 degree angle. So inverse cosine will take 1 over radical 2 back to 45 degree angle. So here, inverse cosine of 1 over radical 2 is 45 degree angle. And 45 degree angle in radial measure is pi over 4. Inverse cosine of 1 over radical 2 is 45 degree angle. And we know that 45 degree angle is pi over 4. Next, subtract. Pi minus pi over 4 is 3 pi over 4. That's inverse cosine of negative 1 over radical 2. Next example. How about inverse cotangent of negative radical 3? How about inverse cotangent of negative radical 3? We know that for these three functions, inverse cosine, inverse cotangent, and inverse secant, when I pull a negative sign, I must add pi in the front. So here, for inverse cotangent, if I pull a negative sign, I must add pi in the front. I get pi minus inverse cotangent of radical 3. Now, radical 3 is a special value for cotangent function. Radical 3 is a special value for cotangent function. For cotangent function, radical 3 is here. That's a special value on the table. Since cotangent of 30 degree is radical 3, inverse cotangent will take radical 3 back to 30 degree angle. Since cotangent of 30 degree is radical 3, inverse cotangent will take radical 3 back to 30 degree angle. So, inverse cotangent of radical 3 is 30 degree angle. 30 degree angle in radial measure is pi over 6. 30 degree angle in radial measure is pi over 6. In general, for these special values, we prefer to use radial measures. 30 degree in radial measure is pi over 6. Next, pi minus pi over 6 is 5 pi over 6. Pi minus pi over 6 is 5 pi over 6. So that's the value of inverse cotangent of negative radical 3. Next, how about inverse secant of negative 2? How about inverse secant of negative 2? we know that for these three functions, inverse cosine, inverse cotangent, inverse secant, when I pull out negative sign, I must add pi in the front. So if I pull out negative sign, I add pi in the front, I get pi minus inverse secant of 2. Inverse secant of 2. Here, number 2 is a special value for secant function. Number 2 is a special value for secant function. For secant function, 2 is here. That's a special value. We know that secant of 60-degree angle is 2. Secant of 60-degree angle is 2, which means inverse secant will take 2 back to 60 degree. Inverse secant will take 2 back to 60 degree. So inverse secant will take 2 back to 60 degree. 60 degree angle in radial measure is pi over 3. 60 degree angle in radial measure is pi over 3. Next, take pi minus pi over 3, I get 2 pi over 3. That's the value of inverse secant of negative 2. Next, how about sine of inverse sine of radical 3 over 2? In this case, sine of inverse sine of radical 3 over 2, we must solve the inner function first. When there are two functions together, we must solve the inner function first. So leave the outer function the same. Solve the inner function first. Inverse sine of radical 3 over 2, what's that? We know that radical 3 over 2 is a special value on the table. For sine function, radical 3 over 2 is a special value on the table. Since sine of 60 degree angle is radical 3 over 2, inverse sine will take radical 3 over 2 back to 60 degree. Since sine of 60 degree is radical 3 over 2, inverse sine function will take radical 3 over 2 back to 60 degree. So inverse sine function will take radical 3 over 2 back to 60 degree. Next, let's evaluate sine of 60 degree. What's sine of 60? Sine of 60 is radical 3 over 2. Sine of 60 is radical 3 over 2. So sine of 60 is radical 3 over 2. That's the final answer. Next, how about inverse tangent of 1 over radical 3? How about tangent of inverse tangent of 1 over radical 3? When there are two functions together, we solve the inner function first. When there are two functions together, we solve the inner function first. So leave an outer function the same. Solve the inner function first. What's inverse tangent of 1 over radical 3? 1 over radical 3 is a special value for tangent function. 1 over radical 3 is a special value for tangent function. For tangent here, 1 over radical 3 is a special value. We know that tangent of 30 degree is 1 over radical 3, which means inverse tangent will take 1 over radical 3 back to 30 degree. So inverse tangent will take 1 over radical 3 back to 30 degree. So what we have is tangent of 30 degree. Next, what's tangent of 30 degree? What's tangent of 30 degree? Tangent 30 degree is 1 over radical 3. Tangent of 30 degree is 1 over radical 3. So if we observe these two examples, you can see that sine of inverse sine of radical 3 over 2 go back to radical 3 over 2. Tangent of inverse tangent of 1 over radical 3 go back to 1 over radical 3. This is not a coincidence. This is not a coincidence. Note, general, for all real number a in the domain of the trigonometry functions, of the inverse trigonometry functions, in general, for all real number a, for all a in the domain of the inverse trigonometry functions, sine of inverse sine of a equal to a, cosine of inverse cosine of a equal to a, tangent of inverse tangent of a equal to a, cotangent of inverse cotangent of a equal to a, secant of inverse secant of a equal to a, and cosecant of inverse cosecant of a equal to a. So if the inverse function is the inner function, then sine cancels inverse sine, I get a by itself. If the inverse cosine is the inner function, cosine cancels inverse cosine, we get a by itself. Since it works for all other functions, that only works if the inverse function is the inner function. That only works if the inverse function is the inner function. If the inverse function is the inner function, then the outer function will cancel the inner function. Sine will cancel inverse sine. Tangent will cancel inverse tangent. That only works if the inverse function is the inner function. But be very, very careful. In general, if the inverse function is the outer function, in general, that's not true. In general, if the inverse function is the outer function, then they don't get cancelled. If an inverse function is the outer function, then in general, they don't get cancelled. That's not true. If the inverse function is the outer function, in general, they don't get cancelled. So in general, that's not true. If the inverse function is the outer function, then they don't cancel. So keep it in mind. That's not true. If the inverse function is outer function, they don't get cancelled. But if the inverse function is the inner function, they get cancelled completely with a by itself. So in 7a, if the inverse function is the inner function, they get cancelled completely with the radical 3 over 2. If the inverse function is the inner function, they get cancelled completely. We get 1 over radical 3. Next example, inverse cosine of 7 pi over 6. How can we simplify this expression? Now, be very, very careful here. In this example, the inverse cosine is outside. Cosine is the inner function. When the inverse trigonometry function is outside, inverse cosine and cosine, they don't get cancelled. Be very, very careful. They don't get cancelled in this case. If the inverse function is outside, they don't get cancelled. Be very, very careful. In this case, we must solve the inner function first. In this case, we must solve the inner function first. What's cosine of 7 pi over 6? What's cosine of 7 pi over 6? For cosine of 7 pi over 6, we can convert from radian measure to degree measure first. We know that pi is 180 degrees. Pi in degree measure is 180 degrees. If I plug in 180 degrees for pi here, 180 divided by 6 is 30. 30 times 7 is 210. So 7 pi over 6 in degree measure is 210 degree. Next, I can try to find a reference angle for 210 degree. 210 degree lies in quadrant 3. For angle in quadrant 3, its reference angle is the angle itself minus 180 degree. For angle lies in quadrant 3, its reference angle is the angle itself minus 180. Here, 210 minus 180 is 30. So the reference angle is 30 degree. And this angle 210 lies in quadrant 3. Cosine function in quadrant 3 is negative. We get negative cosine 30. And we know that cosine 30 is radical 3 over 2. So we get negative radical 3 over 2. Cosine 30 is negative radical 3 over 2. That means cosine of 7 pi over 6 is negative radical 3 over 2. So what we have here is, in the parentheses, is negative radical 3 over 2. Now we have inverse cosine of negative radical 3 over 2. For inverse cosine of a negative value, we can pull out negative sign. Now be very, very careful. For inverse cosine, cotangent, and secant, when I pull out negative sign, I must add pi in the front. So for inverse cosine, when I pull out negative sign, I must add pi in the front. I get pi minus inverse cosine of radical 3 over 2. Then, for inverse cosine of radical 3 over 2, that's a special value. For cosine function, radical 3 over 2 is a special value. In the table, we know that cosine of 30 degree is radical 3 over 2, which means inverse cosine will take radical 3 over 2 back to 30 degree. So inverse cosine will take radical 3 over 2 back to 30 degree. So we get pi minus 30 degree. In general, for special value in the table, we want to run angle in radial measure instead of degree measure. 30 degree in radial measure is pi over 6. Is pi over 6. 30 degree in radial measure is pi over 6. In general, for special values in the table, for special trigonometric values in the table, we prefer to use radial measures. 30 degree in radial measure is pi over 6. Next, take pi minus pi over 6. I get 5 pi over 6. So inverse cosine of cosine 7 pi over 6 is 5 pi over 6. They are not the same. If an inverse function is outside, they don't get cancelled. Be very, very careful. That's an answer for inverse cosine of 7 pi over 6. They don't get cancelled in general. If an inverse function is outside, they don't get cancelled. But if an inverse function is inside, they get cancelled completely. If an inverse function is inside, they get cancelled completely. We get also in the parentheses. Next example. What about inverse cotangent of 7 pi over 4? How about inverse cotangent of 7 pi over 4? Be very, very careful. When the inverse trigonometric functions is outside, they don't get cancelled. In this case, inverse cotangent and cotangent they don't get cancelled. We must solve the inner parentheses first. Solve an inner function first. We must solve an inner function first. Let's solve cotangent of 7 pi over 4. For 7 pi over 4, we can convert to degree measure first. For 7 pi over 4, we can convert to degree measure first. We know that pi radian is 180 degree. Pi radian is 180 degree. If I plug in 180 degree here, 180 degree divided by 4 is 45 degree. 45 degree times 7 is 315 degree. So cotangent of 7 pi over 4 is the same as cotangent of 315 degree. Next, find a reference angle. For 315, find a reference angle. We know that 315 degree lies in quadrant 4. For angle in quadrant 4, its reference angle is the angle itself is 360 minus the angle itself For angle in quadrant 4, its reference angle is 360 minus the angle itself. 360 minus 315 is 45 degrees. That's the reference angle. And we know that this angle 315 lies in quadrant 4. Cotangent in quadrant 4 is negative. So you get negative cotangent of 45 degrees. Cotangent in quadrant 4 is negative, and the reference angle is 45 degree angle. And we know that cotangent 45 is 1. Cotangent 45 is 1. So the inner function, cotangent of 7 pi over 4 is negative 1. The inner function, cotangent 7 pi over 4 is negative 1. Now, what's inverse cotangent of negative 1? For inverse cotangent of negative number, I can try to pull out negative sign first. For inverse cotangent of negative number, when I pull out negative sign, I must add pi in the front. For inverse cotangent of negative number, when I pull out negative sign, I must add pi in the front. So here I get pi minus inverse cotangent of 1. And we know that for inverse cotangent, 1 is a special value. For cotangent function, number 1 is a special value. Since cotangent of 45 degree angle is 1, the inverse cotangent function take 1 back to 45 degree angle. Inverse cotangent function take number 1 back to 45 degree angle. So inverse cotangent of 1 is 45 degree angle. In general, for these special values on the table, we prefer to use radial measures instead of degree measure. We prefer to use radial measures. 45 degree in radial measure is pi over 4. 45 degree in radial measure is pi over 4. For the special values on the table, we prefer to use radial measure. 45 degree in radial measure is pi over 4. Then take pi minus pi over 4. We get 3 pi over 4. So that's inverse cotangent of 7 pi over 4. We get 3 pi over 4. So be very, very careful. If the inverse trigonometric functions is outside the parentheses, then this function need to cancel. If the inverse trigonometric functions is outside the parentheses, these functions they don't get cancelled. Be very, very careful. Next example. How about sine of inverse cosine of 2/3? Here we have one function inside another function. We must solve the inner function first. What's the inverse cosine of 2/3? What's the inverse cosine of 2/3? We know that 2/3 is not a special value for cosine function. 2/3 is not a special value for cosine function. In this case, we cannot solve it from the table. So for this problem, we try to solve it by making one substitution. Let's make one substitution here. Let theta be inverse cosine of 2/3. Let this function, the inner function, be theta. Then, if theta is inverse cosine of 2/3, that means cosine of theta is 2/3. If theta is inverse cosine of 2/3, that means cosine of theta is 2/3. That's the property of inverse function. If theta is inverse cosine of 2/3, that means cosine of theta is 2/3. That's the inverse function property. Now once I make substitution here, inverse cosine of 2/3 is theta. What's in the parentheses is theta. Inverse cosine of 2/3 is theta. Next, let's draw a triangle. Based on this relationship here, draw a triangle. Cosine of theta is 2/3. Draw a right triangle. Assume angle theta is here. That's a right triangle. Angle theta is here. Cosine means adjacent over hypotenuse. Cosine means adjacent over hypotenuse. So 2 is adjacent, 3 is hypotenuse. Cosine means adjacent over hypotenuse. So 2 is adjacent, 3 is hypotenuse. Then here, one side is missing here. For the missing side, we can use Pythagorean Theorem. Pythagorean Theorem says a squared plus b squared equals c squared. Let's call these 3 sides A, B, C. C is always the hypotenuse. So we call these 3 sides A, B, C. C is always the hypotenuse. So plug in. A is 2. B is the missing side. C is 3. Then solve the equation for B. We get 4 plus b squared equals 9. So b squared is 5. B is square root of 5. So the missing side here is square root of 5. So the missing side here is square root of 5. Now, we are looking for sine theta. What's sine theta? Angle theta is here. Sine theta is opposite over hypotenuse. Sine theta is opposite over hypotenuse. I get radical 5 over 3. That's how we simplify this expression. Sine of inverse cosine of 2/3 is radical 5 over 3. Next example. How about tangent of cosecant inverse of 3? How about tangent of cosecant inverse of 3? Same thing. Since 3 is not special value for cosecant, 3 is not special value for cosecant, so we cannot solve it from the table. In this case, we set the inner function be theta. In this case, set the inner function be theta. Let theta be inverse cosecant of 3. Then, by inverse function properties, we know that cosecant theta is 3. Since inverse cosecant of 3 is theta, this function can be rewritten as tangent of theta. We set the inner function be theta. We set the inner function inverse cosecant of 3 be theta. Then by inverse function properties, we have cosecant of theta equals 3. And 3 can be rewritten as 3 over 1. Number 3 can be rewritten as 3 over 1. Next, we draw a triangle based on this relationship here. Draw a right triangle based on this relationship here. Also, angle theta is here. Cosecant is hypotenuse over opposite. Cosecant is always hypotenuse over opposite. So hypotenuse is 3. Opposite is 1. We are looking for adjacent. One side is missing here. We can use Pythagorean Theorem for the missing side. Next, we can use Pythagorean Theorem for the missing side. Pythagorean Theorem is a squared plus b squared equals c squared. Let's call these 3 sides A, B, C. C is always hypotenuse. Let's call these 3 sides A, B, and C. C is always hypotenuse. So here C is 3. A is missing. B is 1. C is 3. Plug in A, B, C. Then solve the equation for A. I get a squared plus 1 equals 9. Then a squared is a. Take square root on both sides. A equal to square root of a. And square root of a can be reduced as 2 times radical 2. Square root of a can be written as square root of 4 times square root of 2. And square root of 4 is 2. We get 2 radical 2. So square root of a can be rewritten as 2 times square root of 2. That's the missing side here. We are looking for tangent theta. We are looking for tangent theta. Tangent is always opposite over adjacent. Tangent is always opposite over adjacent. So we get 1 over 2 radical 2. Tangent is always 1 over adjacent. We get 1 over 2 radical 2. In general, we can try to rationalize the denominator. When we try to rationalize the denominator, we can see that on the bottom we have square root of 2. So I can multiply top and the bottom by square root of 2. Then on the numerator, 1 times square root of 2 is square root of 2. On the denominator, Square root of 2 times square root of 2 is 2, and 2 times 2 is 4. So the final answer is radical 2 over 4. That's an answer in the simplest form. Next example. How can we simplify secant of inverse sine of x? In this case, set the inner function be theta. Set the inner function be theta. So you get secant of theta. First of all, set the inner function be theta. Let theta be the inner function. Set the inner function be theta. Then by inverse function properties, that means sine of theta is x. If theta is inverse sine of x, then by inverse function properties, that means sine theta is x. And we know that s can be rewritten as s over 1. Next, draw triangle. Draw triangle. Assume angle theta is here. Sine function is always opposite over hypotenuse. Sine function is always opposite over hypotenuse. So x is opposite, y is hypotenuse. One side is missing here. How can we find the missing side? We can try to find the missing side using Pythagorean Theorem. Pythagorean Theorem says a squared plus b squared equal to c squared. Let's call these three sides a, b, c. C is always hypotenuse. A and b could be either sides. Let me call these three sides a, b, and c. So here we can see that a is missing. A is missing. B is x. C is 1. Then solve the equation for a. Here, a squared can be rewritten as 1 minus s squared. A squared can be rewritten as 1 minus s squared. Then for a itself, I take square root. A is square root of 1 minus s squared. A is square root of 1 minus x squared. That's the missing side. Square root of 1 minus s squared. Then we're looking for secant theta here. What's secant theta? Secant is always hypotenuse over adjacent. Secant is always hypotenuse over adjacent. So you get 1 over radical 1 minus s squared. Secant is always hypotenuse over adjacent. 1 over radical 1 minus s squared. That's how we simplify this expression. That's how we simplify secant of inverse sine of x. That's how we simplify this expression. Next example. How can we simplify cosine of inverse tangent of x? How can we simplify cosine of inverse tangent of x? So in this case, let's first of all make substitution. Let theta be the inner function. Let theta be the inner function. Let theta be the inner function. So we have cosine of theta. Let theta be the inner function. So we have cosine of theta. Next, since theta is inverse of tangent of x, then by inverse function properties, that means tangent theta is x. Since theta is inverse tangent of x, then by inverse function properties, that means tangent of theta is x. By inverse function properties, that means tangent of theta is x. Here, s can be rewritten as x over 1. Next, let's draw a right triangle based on this relationship here. Let's draw a right triangle based on this relationship here. Assume this angle is angle theta. Tangent is always opposite over adjacent. Tangent is always opposite over adjacent. So that's an opposite, that's adjacent. One side is missing here. We can use Pythagorean Theorem to find the missing side. Next, let's use Pythagorean Theorem to find the missing side. Pythagorean Theorem always says a squared plus b squared equals c squared. So let's call these three sides A, B, and C. C is always hypotenuse. C is always hypotenuse. Let's call these three sides A, B, and C. So C is missing. A is 1, B is x, C is missing. So C squared is 1 plus x squared, which means C is square root of 1 plus x squared. That's how we find the missing side here. The missing side here is square root of 1 plus x squared. Next, let's try to find cosine theta. Angle theta is here. Cosine is always adjacent over hypotenuse. Cosine is always adjacent over hypotenuse. So you get 1 over square root of 1 plus x squared. That's how we simplify this expression. Cosine of inverse tangent of x is 1 over square root of 1 plus x squared.